大家好，我是国立清华大学电机系黄远介。In the last few lectures, we know pretty much everything about transmission line. And in this lecture, I'm going to talk about a graphic tool called Smith chart. And this is a quite powerful tool for you to analyze a transmission line. And as usual, we're going to begin with a few basic concepts. And then we start to work on this Smith chart to figure out, for example, impedance transformation for a line. And we also introduce the admittance because this is quite useful for a parallel circuit. And then finally, we want to see some examples to do the impedance matching so that you don't get reflection from a transmission line. And finally, I'm going to give you a few review. So the basic concept is as follows. So this lecture is all about a Smith chart. And basically, it's a family of gamma curve in the polar coordinate system. And if you still remember this transmission line circuit, we start from a generator. And then there's a transmission line, and finally we have a load for your application. And on this line, in general, there's the reflection signal if you don't have the impedance matching. And we define gamma to be the voltage reflection coefficient like this. And it's a complex number. There's a magnitude associated with it, and then there's a phase angle. And in general, this reflection coefficient is a function of your low impedance. RL is the low resistance, and XL is the low reactance. So if you plot this gamma on this polar coordinate system with the horizontal axis to be the real number of gamma, and vertical axis to be the imaginary number of gamma, then you'll end up having a gamma somewhere here with the angle theta gamma. And if you walk on this transmission line, this reflection angle will be changed. So this gamma is always fall on this circle. And because the reflection signal cannot be more than 100%, so this absolute value of the gamma has to be less than 1. So when you plot this circle on this polar coordinate system, the radius of the circle is always less than 1. And there's a name associated with this circle. We call this SWR circle. And SWR is a short name for standing wave ratio. And this is just the name people call this circle. So in the following, we're going to see this circle play quite important role in the Smith chart. Before I give you the detail of the Smith chart, we want to define some normalized parameters, because when we create a graphic tool, we want this graphic tool to be valid for transmission line with different characteristic impedance. So when we talk about impedance, it's better to normalize the impedance to the characteristic impedance. So now we define this the lowercase z of L to be the low impedance divided by the characteristic impedance. And then now we use the lowercase r and lowercase x to denote the resistive part and also reactive part of the low resistance, of the low impedance. And so now you can rewrite the reflection coefficient as this. Just divide ZL by Z0, and then you organize everything into this form. And this, the small case, the ZL is the normalized low impedance. And of course, you have the real part and imaginary part associated with it. So if you look at this part of the equation, then you can rewrite ZL as a function of gamma. And on the right-hand side, again, this is the real part of your low impedance. And this is the imaginary part of your low impedance. Just copy down from this expression. So on the left-hand side, you have the real part of gamma and imaginary part of gamma. On the right-hand side, you have the RL and XL right here. And just a reminder that previously I already told you that RL in general is large 0, and this is the normalized low resistance. And if XL larger than 0, then we call this inductive reactance. And if XL less than 0, then we call this capacitive reactance. And on this page, I want to emphasize to you that now you can clearly see that the reflection coefficient is a function of your low resistance and low reactance. And later, we're going to specify the value of RL and XL, and then you're going to see that the gamma become a family of curves. For example, now, let's rewrite this expression, and then equate the left-hand side of this expression to be equal to RL. Just equate the real part of this expression to the real part of this expression. And then you'll end up having a family of circles. And if we work out the algebra, then you will be having this expression. And apparently, you can see that this is an equation of circles. The radius of circle is here, and then the center of the circle is this and this. If you set gamma r to be this value and gamma I to be 0, then you'll be looking into the center of this circle. So the point number 1 tells you that the center of circles are on real axis, because I just say that this equation of circles tells you that the center of the circle is located here, and the imaginary part is always 0. So this means that the center of the circles are always on this red line, which is the real axis of this gamma plot. And then now we can look into the radius of this circle, which is the 1 over 1 plus RL. So if you change the value of RL, you change the radius of the circle. For example, if you have the RL equal to infinite, which is the open circuit, then the radius of the circle is going to shrink to 0 value at this point. If you reduce the RL continuously, then the radius of circle is going to increase. And for the larger circle here, this corresponds to RL equal to 0. So this is sort of a short circuit circle on this plot. And finally, if you put the gamma equal to 1, 0, the real part is equal to 1, and the imaginary part is equal to 0 into this expression, this equal sign is always valid. So this means that all the circles on this plot, I'm talking about those black circles, all passing through this point. So perhaps now it's a little bit confusing, but let me just rephrase a little bit. If you specify RL for your reflection coefficient, then you end up having a family of circles, and the center of the circles are located on this real axis, and all the circles will pass through this point, and this point corresponds to your low resistance to be equal to infinite. So if you have an open circuit transmission line, then this is the point you want to look into. But if you have a short circuit transmission line, you'll be having a circle like this, which is the largest circle on this plot. And at this point, between this range of the values, you're going to see that the URL is between 1 and infinite. And for RL less than 1, then the center of the circle is going to be the value of the circle is going to move into this range. Okay, so you can see that the RL value basically give you a family of those bright curves. Now let's try to equate the left-hand side to be the imaginary part of this XL. Basically, you specify an XL. You can also produce a family of curves shown on this plot by blue curves. And again, you can see that this expression is also equation of circles, and the center is located at 1 and 1 over XL. And so this means that the center of the circles will be on this blue line right here. And the radius of the circle is 1 over XL. So if you have for example, short circuit when XL equal to 0, then the radius can be infinite, which is this straight line on this plot. And that is because when you have a radius equal to infinite, then the plot become a straight line. And previously, I already told you that given an RL, you will have those black circles. So when RL equal to 0, it corresponds to the black circles. So this point tells you that the RL value and XL value are both 0. This means that this point corresponds to short circuit transmission line. And also, you might have noticed that for those blue circles, the XL value are all larger than 0. So this part of the XL values are called inductive reactance. And below this, the real axis, you're going to see that the XL values are all negative, and you have capacitive reactance. Now I want to give you one example. And remember that this Smith chart is a gamma chart. This means that every point on this chart will give you a value of gamma subject to your RL and XL. And for this example, we'll have a normalized low impedance equal to 2 minus 1G. And this means that you'll be looking for the gamma value for RL equal to 2 and XL equal to minus 1. And if you just look carefully on the labels of those value on this Smith chart, then you can see that the RL circle corresponds to this one. And as a reminder, I just told you that for a given RL, the circle will have center on the real axis. So this circle corresponds to RL equal to 2. And then next, we want to find the curve, the circle associated with XL equal to minus 1. And so you read on this circle, you can identify that this circle, this branch of the circle corresponds to XL equal to minus 1. And also, you notice that when XL is minus 1, the curve is going to be under the real axis. So at this point, it will tell you the value of gamma due to the low impedance. And so you connect the line from the origin to this point. And remember, a Smith chart is a gamma chart in the polar coordinate system. So the length of this is going to tell you the magnitude of this reflection coefficient. And the longest length is equal to 1, corresponding to 100% reflection. So if you cannot know the length of this, just take a ratio of OP to OR, then you can determine this ratio to be 0.45. And you still have to know the reflection angle. So you extend this line to the edge of the circle, and then you can read from this the edge that this angle is equal to minus 26.6 degrees. The positive angle is above this real line, and the negative angle is under this real line. So now you have determined the magnitude of gamma and also the angle of the reflection coefficient. So you basically complete this solution. So this is one example to find out the reflection coefficient of a transmission line at the low impedance. So in this small section, we introduced what a Smith chart is. Basically, it's a polar diagram of gamma values subject to RL and XL. And for a given low resistance RL, gamma values fall onto a family of circles, and the centers of those circles are on the real axis of the polar coordinate system. And for a given normalized low reactance, gamma value also fall onto a family of circles with center on the line, gamma, real part of gamma equal to 1, and the values of the XL above the real axis will be positive, and the values of XL below the real axis is the negative numbers. So this is the short review for the first section of this lecture. Thank you.